Okay. Okay. Thank you.
So you guys have to study all the weeks. I hope you guys are familiar with uh, week 11 content. Okay, there is nothing to do much with week 12 content of week 11. But I think whatever you have studied in week 12 is you have already studied in maybe in stats 2, right? Statistics 2. The terminology might be different somewhere, but mostly it is the same thing. Okay. So what I'll do is I'm not going to teach everything here in week 12. Okay. But I'll give you the overview of the week 12. What are the important concepts there? I may not go to the derivations, everything, but we'll try to understand what is there in week 12, and then we'll solve some questions, and then yeah, then we'll wrap up. Okay. So uh, okay, so I think yeah, mostly it's not much difficult topic, I'll say. You just know the formulas or the inequalities, for example, uh, and maybe those inequalities will be provided to you in the question paper also. So you need not to remember those inequalities also, but you should know how to use them in the questions. Okay. Okay. So okay, I'm not sure how many of you have seen week 12. Let's start. Okay. So I'm sharing my screen. So have you seen the lectures in week uh, 12?
No, sir.
No?
No, sir.
Sayan, Sharad, you seen, huh? No.
Yes, sir.
Yes, yes, yes.
Yes, sir.
Okay. So fine. Okay. Anyway, if you have seen it or not, it's not a problem, maybe, because I'll do the derivations. Okay, because I don't know. But
We
see,
didn't study the multivariate normal. That concept in stats to everything else it is
yeah,
covered in
it was
stats.
in stats too, right?
Yeah.
Multivariate you may not have seen, but okay, it is generally the extension of bivariate only, right? It's not a different thing. Fine. Okay, it's fine. Okay, let's start with the bivariate and multivariate normal. What does it mean by this term actually? Maybe bivariate normal means what? Can you tell me?
Sir, maybe two normal
Two-dimensional
dimensional normal distribution. Maybe.
Okay, what else?
two-dimensional variance, I
Joint
think.
density of normal distribution of two
Oh,
random variable maybe.
Two random variables. Okay, maybe okay. Let's just talk about maybe bivariate. Bivariate. Okay, you guys are saying this. It's a joint density of two normal random variables. Huh?
Normal random variable, right?
Okay. What about multivariate then? It's joint density of
Multiple.
multiple random.
More than two maybe.
Okay, fine. Uh, what else? Anything else? No. Okay, fine. So let's see what does it mean. Okay, maybe we'll start with this. Okay, uh, anyway, this is correct only, but we'll just see through. Let's say z1 is one uh, normal variable with mean 0 and variance 1. Z2 is uh, Z2 is a random variable with normal with mean 0 and 1, and we have such we have, let's say, d-dimensional ZD is there with normal 0 1, mean 0 and variance as 1. Okay, so if we combined all this variables and into a vector, so how can we write a vector of z? So let's say I have written all this z1 z2 zd. This becomes a d-dimensional vector, and I can say that it's a multivariate you know or multivariate problem, right? Because we have uh, like d variables here, right? If you have two, we'll think about it as a two-dimensional vector. What important thing here is all these z1 z2 zd, they all are what, independent, right? They are not dependent on each other. Okay, so what will be the density of them? So it is denoted by fz of cz. uh, what we can write about it? So
Like individual density.
hmm,
Multiply individual density.
we have to multiply individual density,
Individual density of Z1, Z2.
right? So it will be z1 into z2 to z3. So why we are multiplying it? We are not
Because it's independent, right?
yeah we are not adding it. So generally uh, so yeah, so you know the rule, right? Like, let's say x and y are independent random variables. For example, if they are the two independent random variables, then their joint density will be what? Let's say what should be their joint density?
F of fxy equal to
So I'll write fx into,
fy.
right, when they are
Independent.
right. So here we have d independent random variables, um, uh, independent normal random variables in this case, right? These are not the uh, uh, any other distribution. They are independent normal distributions. So what will be their joint density? Their joint density will be the multiplication of all the densities. So that can be, so each individual density can be written as what? One up. Okay, what is the density of this z1? 1 upon root 2 pi sigma, right? Sigma. So
Sigma
generally
is 1.
it is, yeah. So generally, okay, maybe I'll write down the density of normal distribution. So it is, say MC is equals to 1 upon root 2 pi sigma e to the power minus,
X minus mu the mu x minus mu the whole square by sigma square.
2
2
sigma.
sigma
Oh,
square.
sigma square, yeah.
so it will be fx, right? If I have to write, okay, what else? It is 2
Sigma square.
square, right? So if I have z here, so it should be z, right? Okay. So what is sigma here? It's a
One
function, and
minus one, mu is zero.
so for standard normal distribution, sigma is 1 and mu is 0. So the density of this z1, f of z1, can be written as what? 1 upon root 2 sigma, sorry, root 2 pi, sigma is 1, e to the power minus z1
Z1 square. Right.
minus, yeah, so mu is 0, so it will be z1 square by 2.
2.
Okay.
Mm.
Similarly, what is the density of z2? So fz2 is equals to what? 1 upon root 2 by
2
e to
pi
the power
e power minus z2 square by 2.
by 2. So if I all these things, if I, right, okay, so So the joint density of all of them will be written as like this. So it is 1 upon root 2 pi e to the power minus z1 square by 2 into 1 upon root 2 pi e to the power minus z2 square by 2 into so such that this is 1 upon root 2 pi e to the power minus zd square by 2, right? It's correct, right?
Yes, sir.
We add one page here.
So now we can take the log, right?
Why?
So like we used to do in maximum likelihood, we take 1 by root 2 pi common, and then to solve that product part, we take log.
Not now. Okay, we are okay. That is when we are going to see the parameter estimation, right? Currently, we are just saying what is the density, fine. So fz of z. So this joint density will look like what? So if I do multiplication of all these terms, it will be pi. Pi is what here? It's a product, right? I equals to 1 to d 1 upon root 2 pi. So root 2 pi will be how many times? D times, correct?
Yes, sir, d times.
To e to the power minus let's say 1 by 2 common. I'll have z1 square plus z2 square up to zd square, right?
Yes, sir.
Okay, so this will look like pi I equals to 1 to d. So I can write it as 2 pi to the power d by 2. Why d by 2? Root
Root goes to 1 by 2.
yeah. Okay, and here e to the power minus 1 by 2. So this is like z1 square plus, so let's say if all these are vectors, I can write them in terms of what? Norm.
No. Yes, sir.
So let's
Norm square.
zi square generally. So and I goes from 1 to d. So finally I can write this as 1 upon 2 pi to the power d by 2 e to the power minus 1 by 2 mod of z square. Okay. Because z was the vector including this value, right? z1 z2 to zd. So norm of z will be what? Z1 square or norm of z square. So it is uh, z1 square plus z2 square to zd square, right? That's why I written this term like this. Okay, this is the density of multivariate normal, right? Mm, what else we have to see is maybe we'll see the transform of this normal variable, and then we go to uh, okay, we'll see these things in terms for a bivariate normal in terms of vectors. Okay, so I'll add page here. Okay, so yeah, so let's say if you want to do transform, so let's say z1 is normal 0 comma 1 and z2 is normal 0 comma 1. Let's say these are the two normal random variables we have taken. Now I define two new random variables such that x1 is equals to z1 and x2 is equal to rho z1 plus root of 1 minus rho square to z2. Okay, and the value of rho is in between minus 1 to plus 1. Okay, don't worry about these values currently. Just think about that. I have defined this two new variables x1 and x2 such that they are the linear transforms of z1 and z2, right? This is x1 equals to z1 this is also linear, and x2 is equals to rho times z1 plus, because rho is a constant, so you can see it's a x2 is also a linear transform of uh, two-dimensional normal vector. So this x, can I let's say x is equals to uh, let's say x1 x2. Okay, so let's say this is a vector. Can I represent this vector in terms of uh, or in terms of matrix, this x1 and x2? So x can be written as, let's say I can write this as this matrix, right? 1 0 row and root of 1 minus row of, say, z1 z2. Okay, and z is equals to z1 z2, this vector. So if I write this in terms of matrix form, is it okay? This is the same thing which we have defined here, right?
Right.
So it's 1 minus rho square. Root of 1 minus rho square, right?
Yeah,
Okay,
right.
that's fine.
Okay, so this is the same, but it's this the representation is in terms of a matrix here. So consider this matrix as A, okay, and this as Z. So x is equals to what? Az, correct? X is equals to Az. Suppose A is invertible, then in that case Z can be written as what? uh,
A inverse X.
A inverse X, right? I can write Z in terms of A inverse X. So what will be the inverse of this A? So what is the determinant of this matrix? Determinant of A?
1
Huh? Root of,
by root of here. Okay, yeah. Just determine. Okay.
this is a determinant, and what will be my A inverse? Root of, so this is 1 upon determinant of A, and if I interchange these values inside the matrix, it will be uh,
Root of 1 by.
this will be remaining same.
Hmm.
The, huh?
They have
Sir,
this
the
gap. They have
diagonal
this
entries
gap.
should swap, right? The diagonals would be swapped and the off diagonal signs will be swapped.
1
will
by
be
root of 1 by will be
well,
at first. No, sir.
Sir,
D
root
will
of
be
1
at the
minus rho
place.
square will go to the first, go as the first element.
it will be this matrix. A transpose we have to do, right?
No, sir.
So it's adjoint, right?
Inverses,
Adjoint of matrix.
diagonals, the diagonals will be interchanged.
So principal diagonal elements will be interchanged.
Okay, so this will be like this, right? Upon two, and this one
And the other one will change its sign. Minus
Signs
rho.
will change.
signs will change, right?
Minus rho you'll have.
So yeah, okay. So this will be A inverse. Okay. So, and what is the determinant of A inverse? So it
So
is,
it will be 1 by determinant of A.
1 by determinant of A.
so 1 by determinant of it. This one minus first one. Right. Correct, right? If I do this. Yes, correct. Fine. Okay. Okay. So now,
Hello,
yes.
sir. Uh, Sir, as you said, if it's invertible, but our row is -1 and 1, right? -1 to 1. So if it is -1, then the determinant of this A matrix will be 0. So it won't be invertible, right?
Where did when 1 is equals to what?
The row is equal to 1,
Uh,
then the determinant will be 0 of the matrix A.
okay.
So
1.
it won't be invertible, right? So in that case, we are not able to take, we will not able to take the
I
inverse,
think
right?
okay. These values, right? They should be.
In lecture also, they just mentioned like
But
this
if,
minus
even
1 to 1.
if it's -1, then the eigenvalue will be 0. So it will be still be positive doublet. Yeah, that's why the limit is that way.
No, but if you see, eigenvalue will be 0, but the rank is just 1, no?
Yeah,
in
but
that case?
yeah, like if you see in PCL, we'll still get like those three three linearly dependent like independent vectors. So it will we will be still be able to proceed with it. That's why you're taking it that way.
Not three. You mean to say two
Yeah,
eigenvectors?
yeah, yeah, yeah. Here it's two. I mean,
So,
general.
but we are taking inverse of A, right? We are not like making it that
Yeah,
what we say decompose.
yeah,
We are not decomposing it, right?
yes. The, but here, yeah, here that's true. But like, why we use that limit is because of that.
No, no. We are defining from here, right? We like if we are taking rho as -1 to 1, then it won't be invertible at the corner points, right? That's what main question.
Okay, yeah, you were saying about this, right? -1 and +1.
Hmm.
Or should it be on
That,
open
that
interval, sir?
Okay, I'll check with
Because
this.
what
But
Himanshu
this,
says is
yeah,
right, no?
correct,
Because one,
correct.
if you take the extreme points, they are not invertible.
Yes, and then
Determinant becomes zero.
so let's say if it is 1, let's say 0, this is
No,
Z,
in matrix you will see then
and
maybe.
next one, so Z1. Will that change anything? No, the matrix is not invertible, that is okay, but this case, x1 and x2 will become same, huh? X1 will also become Z1 and
X2.
x2
That's
also.
why the
no,
rank will be one only, not two.
no, in this
Right,
particular
sir,
case,
that and all will be same. In case you take an open interval, will it be correct?
We
Yeah,
have
in
to,
open interval that will be correct.
Yeah.
so I think the lecture, this row condition is for general case, right? He chosen this particular matrix because it's easier to solve this way. Like one, if you keep one element as zero, then it's easier to solve this one. That's why he chose this matrix, and he applied the general condition to here. I think it's not that significant.
So correct. Then in this case, then we need to assume that rho is in an
Yeah,
open interval.
yeah. In order to keep this, yeah.
Hmm. This
yeah.
in order to keep this A inverse true.
Okay, okay, fine. That is okay. Anyway, this only these two conditions, right? Maybe, but
Hmm.
still I'll check.
But in lecture, sir is also taking the close interval. Sir is also
It's okay.
that.
Maybe
No,
sometime.
no, that's what I'm saying. The closed interval will be like a general matrix. Like if you take a general matrix,
Hmm.
there, if even if it's -1, you will still get an eigenvalue zero, and we will still be able to find n corresponding eigenvectors. So it will be fine for that covariance matrix.
Yeah,
But
we will be
here,
able to find the eigenvectors. That's not I'm asking, but
yeah,
uh, we will not A inverse, right? In that case.
Okay, okay. So okay. Anyway, it's okay. We okay. Anyway, we wanted to establish. I understand your point, Himanshu. So what we can do is we'll just see the derivation maybe, and we'll yeah. But maybe you can think about it like that. We are not taking the corner points, okay? Because I think, see, if I take one, then this x1 and x2 becomes the same thing, right? So it's anyway not a linear transformation of two variables here, correct?
Hmm.
So leave about that case. We'll just see. We wanted to find the density of this, right? The linear transform, or maybe two random variables here. So we'll stick to that first, and then we'll try to see other thing. Yeah, but it is noted. Okay, I'll check with this
Okay.
conditions. Maybe the open interval of -1 to 1, but I'll check. Okay,
Okay.
fine. So this is uh, okay. So we were here like z is equals to a inverse of x, and x is equals to az, right? So okay. Then what next we have to do? We need to find the expectation and the covariance matrix, right? For this uh, two random variables. So, what is the expectation of x1? Since x1 is equals to what? It is z1, and what is x2? X2 is like this. So, rho times z1. See, we can have some other matrix also, right? We can have other linear transform also here. Fine, but we are taking this one. It's rho z1 plus rho z2, right? Root of Sigma square. Okay. So what is the expectation of x1? It is nothing but
0.
expectation of z1, and z1 is standard normal, so it is 0, right? Because z1 is having mean as 0 and
1. Variance, yes.
okay. What about expectation of x2?
Same, sir.
But expectation of this term, right?
Okay.
Correct. So that, and since z1 and z2 are independent, we can write them as root. So expectation of rho z1 plus expectation of minus rho square z2. Fine. So this is nothing but expectation of 1 plus of z2. And since both of them are standard normal, their expectations are 0.
0.
Right. So expectation of x2 is also equals to 0. What about the covariance between x1 and x2? I'll write this. Sorry, covariance of x1 and x2 equals to what?
Expectation of xy.
Generally,
X1, X2.
it is like this, right?
Yeah,
Expectation of
x1, x2 minus expectation of x1 into expectation of x2.
right. Okay, this is the formula. Fine. But we know that expectation of x1 is equals to 0
Yeah.
and x2 equals to 0. This term is 0. So here we have expectation of x1 into x2. Okay. So what does that mean? So it's a multiplication of these two random
Z,
numbers. So
z1 into
this term,
rho z1 plus under root 1 minus rho square z2.
right? So this is expectation of rho z1 square plus root of 1 minus rho square into z1 z2. So applying the properties of expectation, I'll have rho times expectation of z1 square plus root of 1 minus rho square into expectation of z1 into expectation of z2, right?
Yes,
Since they are independent, I can write
0 again.
right. So this expectation of z1 is 0 and this is also 0. So this term is 0. So we have rho into expectation of z1 square.
Square.
Yeah, I have to find this. So how to find this? So I know the formula, variance of z1 is equals to what? Expectation of z1 square minus expectation of
Z the whole square.
z1 whole square. Okay. So I need this term. So expectation of z1 square is equals to what? Variance of z1 plus expectation of z1 square, right? Okay. So I think again this expectation of z1 is 0.
0.
So
And variance is 1.
of z1 is 1. So
1.
expectation of z1 square is equals to 1. So what is the covariance then? If I substitute this value uh,
Row.
equation for covariance of x1 comma x2, then I have covariance of x1 comma x2 as rho times
Row.
which is rho. Okay. So this is how we can find the covariance here. So let's say now I wanted to find a covariance matrix for this linear transform. So what should I do? I have to find the covariance, because how does my covariance matrix will look like here? Generally, what is a structure? So on the diagonal, what we have, the individual variances,
Variances.
and on the off diagonals, we'll have the covariances, right? So so we have found out what is the covariance between x1 and x2. Okay, and covariance matrix is what? It's a symmetric matrix, right?
Yes, sir.
Okay. So now I wanted to find the variance of x1 and variance of x2. So again, I'll write what is x1 and what is x2. So x1 is what? Z1. X2 is rho times Z1 plus root of 1 minus rho square times Z2. Okay. So variance of x1 is what? is nothing but variance of z1, which is 1, right? Because z1 is normally distributed with mean equals to 0 and variance equals to 1. What about variance of x2? It is nothing but variance of rho z1 plus root of 1 minus rho square times z2. Okay, so since these two are independent, right? Z1 and Z2 are independent. How can I write this?
Rho square
Variance of
minus
A
rho
plus
z.
variance of B.
We can write like this, or yeah, fine. So let's say if I write this, then variance of rho Z1 plus variance of root of 1 minus rho square times Z2, right? Okay. What is variance of Z1? It's rho times variance of Z1. So which is rho plus uh, what is the variance of, okay, no, it's rho square, right?
Yes, sir, row
Square times
square.
variance of
Yeah.
Z1, right? Plus what about
1
this?
minus row square.
So 1 minus rho square, right? Because we have to square it out, right? Like when
Yes.
it is coming out, that properties we know. So variance of Z2. So variance of Z1, I know it is 1. So this term is rho square plus, yeah, sorry, this is, okay. So what is variance of Z2? This again 1. Variance of Z1 is also 1, right? So rho square into plus 1 minus rho square into 1 is, okay, same. So rho square and rho square will get cancelled. So I'll have variance of x2 as 1. So I know variance of x1 as 1 and variance of x2 as 1. So I can have this covariance matrix of uh, x is the vector x1 x2, right? So this is so on the diagonal we'll have the variance of x1, which is what, 1. Here it is 1 because it's variance of x2. Covariance of x1 and x2 is how much? We have found out in the previous.
Rho.
Row.
So it is rho. So this will be a symmetric matrix, right? Okay. So let's and we have defined one matrix A previously. So this was because I have written this x as A times z, right? So x is equals to A times z. Um, so, okay, sorry. This is, yeah. So what was A? A was 1 0.
1 0 rho root of 1 minus rho square.
So if so, I'm saying that this should be equals to A transpose. So let's check whether this is true or not. So A transpose is what? One row here and 0 root of minus rho square here. Okay. So A transpose will be what? So it's just a multiplication of this. 0 minus rho square, right? So if I do the multiplication, it will be first row first column, which is equals to 1. It's row. It's row. This is it is rho square plus this square, right? So this is 1, right? Correct?
Right, one.
Yes, sir.
Yes, sir.
Square plus root of root. So okay, so this is exactly like this. So I'm calling this as sigma, sigma, which is sigma, the capital sigma. um, this is called as the covariance matrix. Okay. Covariance matrix. Fine. Okay, so uh, okay, now we are here. There are one or two terms we need to find out, which is what is the determinant of this covariance matrix. So I'll say determinant of sigma is equals to what? Is 1 minus rho square, right? Is straightforward. And what is the inverse of this covariance matrix? What is it? 1 upon 1 minus rho square times the adjoint matrix. So yeah, tell me what should be. It is 1 1,
Minus rho minus rho.
right? Okay, correct, right? 1 1. So
Yes, sir, it's correct.
okay, so uh, we know like mostly what is A. So I'll summarize it once again. What we need to find the density. So what is A? A is 1 0 rho and root of 1 minus rho square. From this A, I found the covariance matrix, which is geometry by sigma, that is equals to what? 1 rho 1, right? Then I have determinant. I'll write this. Determinant of this is equals to 1 minus rho square. Then is inverse of this matrix is equals to what is it? 1 upon 1 minus rho square and 1 1 minus rho minus rho. Okay, these things are there. Okay, okay. So now I wanted to find the joint density of x1 and x2, right? So how to find that? So fx of x, I'll write what it should be, or yeah. So how should I write this density? So I know that x is equals to what? Az, right?
Right.
So let's say so z is equals to what? It is a inverse x, right? Hmm?
Yes, sir.
So can I write fx of x as uh, like this, side of a inverse x. And what is x actually? So x is some matrix times z. So it's a linear transform matrix, right? So times into determinant of a inverse. Can I write like this?
Sir, I don't understand how you wrote X.
Sir, why this determinant of A inverse?
Yeah, think about. So we
Because
have
X is
We studied in the week level, so it's in Jacobi. It's the same.
hmm?
We did it study in the last week,
yeah,
like
yeah.
week 11, there is a Jacobian thing, like, when we transform this A trans, yeah. Simon wrote it in the chat. It's just the determinant of the Jacobian.
You have seen that, right?
Yes, it was in the last week.
Last week 11, right? So fj of this term and it, times the determinant of a inverse. Okay. So I think and one more. Okay.
Sir, how this is? Sir, how they both are equal? Like I didn't get this. I know it's Jacobian, but I'm not able to understand.
Okay, just a minute. I'll just write down one more thing. Is we haven't write this yet. What is A inverse? A inverse is we have determinant. Determinant is in form
1 upon under root of 1 minus rho square.
1 by 1,
this.
Rho square.
0,
And 0.
0 minus rho 1.
So,
So it's 1 0 is okay. So this is what is determinant of A inverse? I think that for determinant of A inverse, I need not to do this, right? It is determinant of A was equal to root of 1 minus
1
rho.
minus rho square.
Determinant of X is 1 minus.
Determinant of A. Yeah.
So Yeah, this property we. Okay. Uh, what else? So now we were here, right? So I know that uh, x is equals to a times z, right? Uh, okay, and I said that okay. Generally, how you write this fx of x? Okay, so let's say if I wanted to find the density of fx of x, how you are going to approach it? Hmm? I have two things, right? So I have x equals to az, and I can write z as a inverse of x. Okay, a inverse of x. Okay, so if I wanted to find the density of uh, uh, x, can I write it in terms of z?
Sir, are you using that transform term?
I think we have seen that in stats too also, right? Or no? Uh,
No idea, sir.
No, sir, it was done only in week 11.
So
what?
Jacobian,
Transformation.
yes,
Uh,
transformation in we do in week 11.
Okay.
we
We
only
do transformation and then multiply with the Jacobian matrix for
that's true.
density. Yeah.
Okay, so what you did in week 11 is, okay, we'll recall that one first. So what you do, this is, okay, tell me
Sir,
first.
is it something like functions of random variable?
Okay, you tell me now, one, maybe what you learned in the, give me one example of it and we'll try to, transfer it to this. So from week 11, any example do you have in the week 11? Any
Sir,
other?
there is only one example in week 11 which Sir took it. Otherwise, we don't have any example in that, not in GA, not in PA, not in activity. In activity also, we have only one example. For that, they have asked to do the Jacobian matrix. But as such, whole and soul, where we have to calculate, we have to transform and find out the density, there is no such question,
Okay, so there is only one example which is
which
there.
Sir has taken in the lecture.
But did you understand that one?
So that part, finding out the density, I understood, but the range part, which madam took it through figure, which that one is not clear yet for me.
Okay, so you
If
wanted
it is
to.
a simple range, then I can take out. It's
Okay,
not a problem. But for that question, the range was not easy for me to take out.
Range, we did the same thing in stats, so it's the same thing. We are doing the
Yeah, it
same
was
thing.
easy, but what we have done in stats too, because it was very much direct, like we have to just substitute the values and find out. But in that
Yeah,
question, I don't
here,
think it was so simple.
okay,
here
fine, fine.
also we
So
are doing.
yeah, yeah,
No,
yeah. You guys can.
no,
Yeah.
no, sir. We got like the corner points, right? Here, what ma'am did was like we got the corner points,
Hmm.
and
And
like
whatever is there in, is it in between, right?
yeah, it will turn into a parallelogram. Like that's what Professor was also saying. But even if you don't do it that way, if you just take the corner points and convert it, like whatever function that's given,
Hmm.
using that, if you convert it and if you look at the
Yes. Uh,
graph, you can still see it. Like
okay,
like
so okay, I understand, but okay, fine. So, but I think again it will take a lot of time for us to understand, right? Maybe I'll see if I get the time. I'll try to find it. But okay, and okay, in total, I understand that. Okay, you guys don't know how to. Uh, Maybe you know it, but it's not very clear because we don't have the enough examples there, right? In like how to be write this kind of density. Okay, for now, for completing this derivation, let's see, we can write it in this terms, right? Okay, f of z of let's say this a inverse of x, because okay, let's, I don't know, it will take time, right? Okay, fine. So okay, just understand now, maybe we'll try to explain you with more examples of these transforms. Okay, and how to find the range and everything. But for now, you just understand that f of x I can write in this term, okay, in terms of z, and that is of uh, we have to find the determinant of A inverse. Okay, don't worry about this. We'll study this also. It's not a problem. Okay. Okay, so this fz of A inverse of x, and I can write in this term. Okay, I'm saying that okay, we can write this. This for now you just understand because anyway, this is a part of a derivation. It's not going to come into like anywhere. But I understand this is an important topic to understand that how to find the densities of this transformed variables. Okay, fine. So what is determinant of A inverse? This is we have already written here. So fine. So I can just write the density like this. So fg of A inverse x. How can I write this density at least? Can you tell me this density? What is A inverse x? Hmm? Okay, what is x here in this case? X.
X1, X2, the vector. So
It's a vector, right? It's x1, x2, right?
So we will do like we'll write x1 in I mean x inverse into vector x1 x2.
Right.
Is
So this is a vector. So
yeah.
and again x1 is what? X1 is a function of z1 and
Yes.
z2, right? X1 and x2 are the functions of z1 and z2 that we have already seen. We have started with that only.
Yeah. So whatever we have calculated, like
This
we
is z
cannot.
only, right?
Yeah. Z1.
Right. That's why I'm able to, since x is equals to az, and now okay, I'm trying to say that uh, x is az. So whatever this term is there, again it is in terms of z only, right? This is correct, right?
Yes, sir.
So since see x1 and x2 is nothing but some matrix A, okay, it's a it's coefficient matrix, right? And we have what z, we have this vector z1 and z2. I'm what I'm doing right now is I'm just saying that z1 and z2 can be written as A inverse of x1 x2.
X2.
Okay, so I'm just kind of like writing like f of x is equals to, let's say, some constant times z, right? Then f of z will be what? It's like 1 upon c times f of x, right? Right.
Okay.
Right. So that is what we are trying to do here. It's not a different thing. You can see here, right? So this is the same kind of like if you see the functions, but here we are not dealing with functions. We are dealing with vectors, right? That's why I have to write in this manner. Okay. So fz of A inverse of x. So x is actually what it is. Uh, it's 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 a function of z1 z2, right? So if I wanted to find the density of this, how will I write? So this is, and what z1 and z2 are, they are normal random variables, right? Correct. So their density can be written as in terms of normal variable, right? Uh, so it will be written as so this determinant of A inverse is 1 upon root of 1 minus rho square. Okay, and fz of A inverse x. So z is actually a normal random variable. So how do you write the density of a normal random variable? So look this as fz of z. So what is z here is it's A inverse x. Okay, z here is A inverse of x. What is f of z of z? It's 1 upon
So 1 by root
2 pi
2 pi
hmm,
sigma square, that is 1,
okay, sigma square into
e power
minus,
minus half, yeah, by 2 sigma square.
right? Okay, this is the this is the density of z when it is a
Yeah.
normal variable. But here, what is z? It's A inverse
A 6.
x. A inverse x, and sigma square here for us is 1, right? right?
Yes.
Because this is standard normal zero. So it will look like what?
And mu is 0.
Mu is 0. So it will look like this, z square
Yeah.
by 2. But what is z square?
A inverse.
A to the
Sorry.
power minus is a inverse of x
A inverse of x
by 2. And it's a square.
square.
Okay. Right now. But this is not a term, right? This is not like single term. This is a vector. So generally we write vectors vector square as what in terms of norm.
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 So that's why we write this density as this density, because these are vectors. We are not talking about the uh, simple r to r functions, right? It's a vector, so we have to write it in this term. So can I rub this one? This fine, right? You just understand this part at least, right? Yeah. Why we can write generally how we can write the density of normal random variable. So I'm just so how will I write this density? This this term is determinant of A inverse. So this density I can write it 1 upon root 2 pi e to the power minus 1 by 2. Okay, this is okay.
Yes, sir.
So this I can write. So this can be written as again 1 upon root of 1 minus rho square 1 upon 2 pi e to the power minus 1 by 2. Okay. Mm, okay. Until this is okay. No. Okay.
Sir, is it not root 2 pi?
Sorry.
Is it not root 2 pi?
1 upon root 2 pi.
Uh, you have just written 2 pi, right?
So it should be root 2 pi. No?
Yeah.
It's 1 upon root 2 pi sigma square. Sigma, right? 1 upon root 2 pi sigma e to the power. Right. Okay, fine. This is okay. So we can write this in terms of transpose and can I write like this transpose and A inverse of x? Because generally uh, what is this?
Norm. Norm is
There is
A
what?
transpose A.
Yeah. So let's say if it is
Yeah.
A, then it can be written as what? A
A
transpose.
transpose A.
Right? So let's say in terms of instead of A, we have A inverse x here. So I can write this as A inverse x transpose into A inverse x, right? And if I have this transpose inside, then it will be x transpose A inverse transpose A inverse 2x, right? This is a term, right?
Yes.
Okay, and this term I can write as x transpose. Can I write like this? A inverse, uh, or maybe A transpose inverse. So right, and into x. I can write this as, or not, sorry, not this one. Oh, sorry, this one. A inverse, right? Square. Correct, right? Is okay?
Yes, sir.
Okay, so I'll just write down this term here, root of 1 minus rho square 1 upon root 2 pi e to the power minus half, and this term. This term will be what? X transpose A transpose inverse into x. So you can think this about, so what is AA transpose? That was my,
Sigma.
yeah, that was my covariance matrix, which was what? I forgot. Is it 1 0? Sorry, I think 1 1 row. Yeah, right. This one. This was AA transpose, right? So it is 1 2. Okay, fine. Uh, and what is the inverse of it? Sigma inverse is equals to, okay,
1 by 1 minus rho square.
rho square 1
1 minus rho 1.
rho. So substitute all these things here. I'll get root of 1 minus rho square 1 upon root 2 pi. We are actually trying to find the density of x here. Okay, so this is 1 by root of e to the power minus half times what is x? X is a vector, right? And x transpose is what?
x1 x2.
X1 x2. Okay, uh, and then what is a transpose? It is, say,
The same sigma 1.
then we will write the constant out. It is root of 1 minus rho square 2 right, 2 into this, and into 1 minus rho
Minus rho 1.
and
x1 x2.
yeah, it should be like this. Okay, this is a kind of a matrix problem, you can see, right? Like, yeah, so we have this kind of matrix here. So, okay, then I wanted to prove that this f of x is uh, okay. Maybe I'll just go a few steps ahead. Okay, so start with, okay, this is in terms of the vectors. So try to solve this. 1 upon root of 1 minus rho square is 1 upon root 2 pi, and let's say this is e to the power minus 1 upon 2 times 1 minus rho square. Okay, if I try to solve this this matrix, what it will be?
It will be x1 square plus x2 square.
Have you solved this one? Okay,
Yeah, x1 square plus x2 square minus 2 row x1 x2
x1 square plus
x2 square
x2 square minus
minus 2 row x1 x2.
2 row x1 x2. Okay, so if I do this, all these terms here, root of 1 minus rho square, root of 2 pi, then e to the power. So if I multiply this constant here, this will be what? E to the power minus x1 square by 2 times 1 minus rho square, right?
Right.
Is correct, or is correct, or there is a mistake? Can you just check once?
Minus 2. Yeah, it's correct.
Okay, let's see. Okay, fine. And what about this? Uh, the next term will be what? Uh, x2 square,
Divided by minus.
or
So it has to be minus.
okay, this is, maybe you do one thing. We'll make this into two separate terms, right? So let's say I have taken x1 common, x1 square common from these terms. Will that work or no? Mm, okay, fine. I will just do this 1 upon e to the power minus 1 upon 2 into 1 minus rho square x1 square minus 1 upon 2 1 minus rho square x2 square minus what is it 2 to
Plus
rho
Plus.
E plus.
rho square and x1 x2. Okay. Okay. So actually, I just wanted to uh, show this that these two densities we can write in terms of conditional density and the conditional density of x2 with respect to x1 and of x2 and this multiplication of the two densities like that. So I'll just write down this formula. Okay, I'm not doing okay, let's see. Right. So yeah, just tell me once f of fx of x is equals to 1 upon root 2 pi into 1 upon root of 1 minus sigma rho square e to the power minus x1 square by
2 into 1 minus rho square.
1 minus rho square. Then we had plus no sorry minus x2 square of 2 into 1 minus rho square plus rho upon 1 minus rho square x1 x2. Okay. Okay, so do one thing here. Maybe okay in this term, right? In this term, let's try to extract x1 square. Uh, okay, x1 square out of, or maybe take the common. So I don't think we have to do that. So let's say 1 upon root 2 pi, 1 upon root of 1 minus rho square. Okay. I think we have done some mistake somewhere. I guess I'm not sure where. Okay, let's leave it. 1 upon root of 1 minus rho square. If I take something common here, x1 square common, so it's 1 upon 2, here it is 1 minus rho square, okay, into, this was the thing, right? X1 square plus x1 x2, sorry, and x2 square. So what I'll do is, I'll just somewhere,
It will be minus 2 rho, no? I think.
sorry,
It will be minus
x1 x2,
x1, yeah, minus 2 x1 x2, maybe.
minus,
And row is also there, right? So 2 row would be there.
Minus
2 row
2
is
rho. Yeah, minus 2 rho.
minus 2 rho. Yeah, this is the expression, right? Okay, I don't know. I think somewhere I lost 2 rho x1 x2. Okay, so the part is I wanted to show that this is f of x is equals to this is can be written as f of x1 times uh, x1 of x1 times
How Professor did is he directly substituted for z as
correct.
x1, uh, and from there, like, he split the terms.
Hmm?
He directly substituted for z in that term, like a inverse x, right? That term.
Hmm.
He substituted it as x1 plus rho. The second term z2, z1 and z2. He substituted that, then squared it, and then split the terms.
But it's the same, na? Or this is different thing.
Yeah, it's the same thing, but I don't know if the sum is correct, like from where you're trying to do.
Somewhere because yeah, he what he did is I think sir has done this is like 1 upon 2 pi root of 1 minus rho square, and I think we did like this, right? Minus 1 square. I think he has squared this term only, right? A inverse x.
Yes, and then he put it like x, yeah, x1 square plus uh, rho by that plus x1 plus 1 by root of 1 minus rho square x2, and squared it. That way.
Mm, I think here also we can do the same thing, but I'm not sure where the factorization can be done. Yes, madam, I'll just check
So
once.
he has taken A inverse X in the matrix form and found the norm. How do you find the norm? Square of the vectors. So that is how he has done it.
The same thing, right? Explain.
Yeah, but I think just do the calculation and what maybe it's there is a mistake.
But I forgot to check here, right? Yeah, this matrix, I'm, can just check once. I'll just check here.
It's
X1, X2. Let's say this is 2 by 2. This is cross 1. So I'll get vector, right? This vector will be x1 minus rho x2 is minus rho x1 plus x2. Okay. And it's 1 cross 2. This is 2 cross 1. So I'll get 1 by is x1 times x1 minus rho x2 plus x2 times minus rho x1 plus, so something like this, right? x1 square minus rho x1 x2 plus minus, correct only, right? And x2 square. Mm, this is correct. Think about this one. X1 square minus 2 rho x1 x2 plus x2 square is okay. This term is fine until this is okay. But I say e to the power is constant. Right? Square. Uh, or minus x1 square by 2. Right? Minus or not minus. This should be e to the power. Hmm. Okay, I don't know. I'll see. Uh, Maybe I'll write down the end results because one term, one extra term is coming here, right? Which is x1 square. This one. I don't know where it is coming from. Do you understand any problem here in this derivation? Okay, I think so. Okay, it's okay. Maybe we should not waste the time. Uh, I'll see if anything comes up in my mind. I'll just show that one. Okay, I'll write the end result. I think that will be good. That's not a problem. So yes. So let's say f of x, fx of x can be written as the density of fx1. Okay, I'll see my problem. Right? Okay, where I did the mistake. If it is there, I'll just maybe I'll write down the document and we'll share with you uh, of the derivation. So fx1 of x1 into this should be the end result. Okay, this should be the result fx2 of, so the conditional distribution of x2 with respect to x1 of x2 given x1. Okay, and if you see it should be, what is fx1 of x1? It should be 1 upon root 2 pi e to the power minus x1 square by 2, right? So this x1 square by 2 into 1 upon and what should be the conditional distribution of x2 with respect to x1? It should be like this. I'm telling you, it should come like this, e to the power 1 upon root 2 pi 1 minus rho square into e to the power minus 1 upon minus rho square x2 minus rho x. I'm just writing down the end result. um, I'll share you the exact derivation of this one. Okay, I don't know where, somewhere I did the mistake. Maybe I don't know. I'm not able to rectify now. Okay, so and this should like look like this. Okay, this is the density of, this is the conditional density, and this is density of x1. Now this should be normal with what, mean equals to 0 and variance equals to 1, right? Because okay, anyway, this fx of x1 is nothing but what, fz of z1 only, right? Because x1 is equals to z1, and what is x2? X2 is rho z1 plus root of 1 minus rho square into z2. So if I write down the conditional distribution, this distribution should have, this is also behaving normally with mu equals to rho x1 and variance equals to 1 minus rho square, right? Square of this term. Okay, so if you have given the linear transform in this fashion uh, of the two random variables, their joint density can be written as fx1 of x1 and to fx2 of x1. Okay, this you know, right? Like this, generally for two random variables we can write the joint density like this. We have studied that in the stats too. The only thing is if these two random variables are uh, normal and it's a function of a random variable, I can say, or the transform of the random variable. In that case, their uh, distributions, right? It will look like this. So that is the main point of it. I know I did some mistake somewhere. I'm not sure where it is, but I'll try to rectify it and share the solution with you. Okay. Now the things which we should look at is what okay, so I'll just write down some results. I'm not going into the derivation part. So I'll and we'll see some inequalities. I think central limit theorem also all of you know, but let's see. So let's say for multivariate normal, so we have seen that result right now. I can extend that result of density for the multivariate normal. Anyway, those derivations are not much useful, but still they are the good part to understand what is the density, like how to find the densities. So maybe I'll share that with you. Don't worry about it. It's not a big problem. Okay. So x is equals to az plus that's mu. So if x is some transform linear transform of the z, right? So z is actually here. It's not this a is what it's a matrix, right? And z is a vector. So if is x is a is matrix, z is d-dimensional vector maybe, and mu is what? Mu also should be a vector. If this is the case, then we have the density. So this is a multivariate normal case. So z is actually z1 z2 to zd, let's say, and all these z1 to zd are independent. They are independent normal. Okay, independent normal vector. And what kind of normal? 0 1. Okay, so if this is a scenario, then in that case my density will look like this: root of 2 pi power d 1 upon root of sigma of sigma and e to the power minus half x minus mu transpose minus this we have seen that for the bivariate case it was like x transpose, then what it was, a transpose inverse, right? So a transpose is nothing but what covariance matrix and times x. So this is the same thing we have written, only in that case we had x is equals to az, right? If you have added one term mu here, then this will look like this. Okay, so here we have extra vector, the mean vector. That means we are shifting the mean, right? We are shifting the mean. The mean is not zero. If it is away from zero, in that case this will look like this. In this case, expectation of x will be what? So it's simple, right? So because x is equals to az plus mu and z is having mean 0, then expectation of x is what? Normally it should be e times az, right? And plus uh, mu, right? Because it's a constant. So this is expectation of z, right? So anyway, I can take it outside, and z is 0. So 0 plus mu. So expectation of x will be equals to mu. But here it's not a single or scalar; it's a vector, right? So expectation of x is mu. What about covariance matrix? Covariance of x, which is denoted by sigma, it should be equals to what? Is A transpose. Fine. Okay. And this x is distributed normally with mu, with mean mu and variance. So that variance is not, it's a covariance matrix. So mu is a vector and this is a matrix. This vector, this matrix. So what are the dimensions of this? So mu will be d cross 1, right? Because we have z from z1 to z2. And what about covariance matrix? So d cross d matrix. And what are the properties of this matrix, the covariance matrix? So the covariance matrix is, okay, this is obviously a symmetric matrix, right? symmetric matrix, and it will be a positive definite matrix. Okay. Uh, okay. What else we can show is, okay. So yeah, we have to see the parameter estimation also, and we will see that one. Yes.
Yeah, the lecture process says something like if xi and xj are two independent random variables and so
Uh,
their covariance will be zero.
uh,
But if they are normal, it will hold in the opposite. What does he said? It will hold in the opposite direction to what does he mean by that?
no. Can you repeat once? What is?
He said, if xi and xj are like two random variables, if they are independent, in general their covariance will be zero, right?
If they are independent, their covariance is zero.
And he says if they are part of a multivariate normal, then this will hold in the other direction also. That's what he said in the lecture. So
Other direction means where?
that's
Like,
what I didn't understand.
It will
Like,
be if and only if, sir.
does it mean
The
like
reverse is all, the
if
converse is also true.
means if two xi and xj are part of a multivariate normal and if their covariance are zero, then they will be independent. Is that what you mean?
okay, so okay. Conversely, if it is true, huh? Okay.
I don't know, sir. I'm asking. Like, is that what professor? I don't.
That's what professor said, sir, in that lecture. Properties, one of the properties.
Okay, so that's what he meant. Like if they are part of a multivariate normal and their covariance is zero, then they will be independent.
Okay. So when xi and xj are independent, that means definitely their covariance is zero. That is correct, right? But you are saying if the covariance is zero, then they should be independent, huh?
So if
Yeah,
they are part of multivariate normal,
Multivariate normal. Okay. I'm not sure. Like, okay. I don't know the maybe maybe some proof will be there. I don't see like it is wrong, but I don't know how to prove it that way. Covariance of,
okay.
okay. Okay, we'll see. These are the properties, huh? Just a minute. I'll just give a minute. I'll just come back. Huh? Just give me 5 minutes. I'll just come back. Let's see some. Sorry. Okay, let's see some parameter estimation thing. Then I'll write down some inequalities. Okay, and center limit theorem. So parameter estimation. Uh, just try to recall, and then we'll see one method here. Because this course is having only one method for parameter estimation, which is MLE, right? What is MLE? Maximum likelihood, right? Sorry. Okay, so in general, what will be the scenario when we see some random variables, right? So let's say you have a distribution and you have taken a sample from that distribution, okay, and you wanted to find the parameters of that distribution. For example, what, let's say x1, x2 to xn are the IIDs. IID maybe, let's say Bernoulli. Okay, Bernoulli, and what is the parameter in Bernoulli in case of Bernoulli distribution? It is one parameter, right? Which is
P.
p, probability of success. Okay, so what what we wanted to find is here it's or what we're trying to estimate here is p, right, the parameter which is there, which is unknown to us, right? In general, let's say we are thrown, let's say, uh, like heads, okay, or if I have a coin and we know that that coin is having like it's Bernoulli distributed. Okay, means like whenever I toss a coin, I know there is a certain probability of getting a head. When I say getting a head is a success, in that case, I know that it's some p, right? But I wanted to calculate p. How to find the p of that toss, right? So in that case, what helps us is this the parameter estimation, right? And how to do that, that you will see, right? Okay, so in general, I'll write down one some, so let's say I have a coin, and if I toss a coin, right, this coin will have certain probability. So let's say P is a probability of success, right? Let's say this probability of success, and I say this coin is uh, having the Bernoulli distribution with probability of success is P, but I don't know what is a P, because let's say you have a huge population, right, and but you cannot be sure about that probability. So how do you do, like how do you find the parameter in real life scenario? What you do is you just throw some or you do some tosses, like a certain number of tosses of that coin, and you note down when the head comes, also probability of success. And in this case, let's say I said head is a success, okay, getting a head, head is success. Okay, so let's say if I toss 10 tosses, so so toss a coin 10 times. So I got like head, tail. What is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So can I write this as uh, say, but this is one toss. Can I write this as some or this is the entire sample, right? This is a sample, right, of the, let's say we can have more number of tosses, but I'm saying that okay, uh, this is one toss, and I can say for each time if I toss a coin, this is distributed with Bernoulli, right? We're gonna be with some p. I don't know, right? I don't know that p. I wanted to find that p. So if I do, and this entire thing is one sample, right? Like, in that case, how many heads are there? 5 heads are there, and 5 tails are there. But if in this case, in this 10 tosses, I got 5 heads and 5 tails. So can I say the probability is equals to 0.5? Is it a correct statement or wrong?
Yes.
Okay, think about it once more. So can I say
Correct.
this parameter is p equals
Correct,
to
sir.
0.5? Is it correct?
Yes.
So let's say if I have another sample like this of the same coin. In this case, this is another sample. Let's say, what is the probability?
0.3.
0.3. So, and if this is the same coin, so now what is happening here? So okay, but that means, okay, this can be okay. Here, what is happening here? It's actually the probability. This probability of success, right? It is also a random variable. Like, the p is a random variable. We can actually find it for the constant p also, but here we are saying that it's a random variable, right? Each time the probability of success is changing, and I wanted to find that p for the entire distribution, right, or entire population, right? So we just find out some samples, and based on that sample, I will try to find what is the theta, what is the probability of getting. So what I'm saying is, let's say, given this sample, okay, or given this data, what is the probability that p is equals to 0.5? Okay, then for given this data, what is the probability that p equals to 0.3? Given this data, what is the probability that uh, it is equals to 0.1, right? And in this all these things, let's say, what is the probability? Let's say we have probability of this as 0.3, uh, right? And let's say it's 0.2. Let's say this is 0.1. So maximum likelihood estimate will go for which value?
0.5.
0.5, right? So then I will say that this probability of uh, uh, of of this data, given that p is equals to 0.5 is 0.3, and hence I'm saying that this parameter, the estimated parameter, is equals to what? 0.5. Okay, so this we do with the maths, and how to do that we'll just see. Okay, maybe you guys have seen all this in stats too already, so just write down the method, like how to solve this. Okay, so let's say you have some data x1, x2, xn. These are all IIDs. Okay, IIDs means what? Independent and identically distributed uh, uh, samples, right? So these are the samples. Okay, so these are identically distributed. Identically distributed means each of xi will have the same distribution. Independence means each time that so x1 is not dependent on x2. So whatever the results is coming for x1 or x2 is not dependent on what has happened for in x1, right? So these are IID samples from certain distributions. What we wanted to find is, given this distribution, okay, given this sample, sorry, not distribution, and let's say some x, right? We have taken some samples out of a distribution, and given based on that sample, I wanted to find what is the parameter of this x, right? So then, in general, what is the case? It's x1, x2, and xn. Okay, or maybe I'll say this was the sample, right? So head, head, tail, head, tail, head. 1, 2, 3, 4, 5, 6. Tail, tail, 8. Okay. So let's say this is a sample which belongs to Bernoulli P, right? And all these are ID samples, or I'll say this which belongs to ID Bernoulli. In that case, can you tell me? Can you tell me? Or okay, so and then I'll say that what are the successes? So head is a success. In that case, I'll write this as 1 0, right? In terms of 1 0 0, say 1 1 0 0. So okay, so I'm saying that this is a sample drawn from this distribution Bernoulli P. Okay, I wanted to find the estimate for this. So how to find by using the maximum likelihood method, MAD method is this. So what is the likelihood? So okay, currently forget about this. I think about this. Yes, okay. So likelihood is given as the likelihood of this is given as what? Probability that given this data, so no, probability that this data and given this parameter theta, right? So I wanted to find this one, which is nothing but probability that x1 x2 x1, which is okay. These are let's say these are the samples, okay, given that data. So this is given by maybe I'll write this as x1 equals to x1. So what is capital X1 and what is the difference between this capital X1 and small x1?
Capital X1s are the random variables, and small x1s are the values that the random variable takes.
X, right? So yeah, and capital each capital XY is what? It's P, right? Okay, okay. So not per ID, ID, some parameter thing. Okay, so okay, so if they are independent, right? If they are independent, how can I write this statement?
So if they're independent, their PMF or PDFs would be same. So we can just take a product.
Product, take a product of this. So this will be the product of I equals to 1 to n fx I of xi theta, right? Given that this parameter theta, this is what uh, likelihood of this. So there are 2-3 methods to solve this. So in generally, what how to solve this problem is we can take a log of it so that this will become a linear problem, and then equate it, and then we differentiate it and equate it to 0. So generally, it will be we'll take the log likelihood. So log likelihood will be what? Log of this term. So this term I'll write as maybe yeah, so uh, okay, so let's say some uh, mm, okay, I'll tell that it is log of pi equals to 1 to n xi of xi given this, and then what you do is you just differentiate this log likelihood with respect to theta, log of theta to 0, right? So this is a maximization problem, right? We'll see that. So we can say that whatever the value I'll get with differentiation, that will be the maximizing or will have that maximum probability that for this theta, uh, for given theta, this will give me the maximum probability, right? This is one way, or the another way is minimization of this, right? So how do we do that? I will take the negative likelihood of this. So negative log of theta should be equals to minus log of this term, yeah? Minus log of name theta. Okay, and then I take uh, the different the derivative and I equal to 0. Right? Is the minimization of negative likelihood. Both of them will give me the same result. So let's try to find out for you know one or two variables, uh, maybe one discrete variable and one continuous variable. Then okay. So let's say the normally we'll find, so one case will be Bernoulli, another I'll check with Bernoulli, and another will be, let's say, exponential. Okay, how to find this? So first I will say for discrete, right? So let's say uh, is it x1 x2 up to, let's say, xn is IID Bernoulli with parameter, say p. How to find it? So I think in MLF we, I think professor has done it with negative log likelihood. We'll try to do that. Both of them will give me the same results. Okay, so let's try to find out its likelihood first. So what will be the likelihood? Okay, what is Bernoulli p? So what is the density function for this Bernoulli random variable? Is equal to p if x equals to 1 or head, right? And 1 minus p if
X equals 0.
0. Okay, so if my likelihood will be, let's say, it's in this term, it's p. Okay, so it will be what? Hmm? This is the product, right? So it should be product of so let's say we have x1 to xn, then suppose I'll say p to the power, we have, let's say, some x. Okay, we have p to the power x, and uh, then
1 minus
to
p,
the power n minus x,
n
Minus.
minus x.
right? Because we have n uh, samples right here. Okay, so this is my uh, likelihood. So what will be negative log likelihood? First of all, okay, first of all we'll find out log likelihood, which is what? X into
Log of p. um,
x of log of p uh,
Plus 1 minus x.
plus n minus x log of 1 minus p, right? And what is negative log likelihood? Okay, you can have the other method also. Okay, I'm not saying that this is the only method. You can solve it other method also. So choose minus of uh, x log p, right? Or and minus of n minus x. So okay, I can solve dp, right? Wait. So yeah, it will be what? And I'll equate it to 0. So minus of x upon p, right? Minus of minus x upon 1 minus p minus 1, right? It should be equal to 0. Correct?
Yes, sir.
So if I try to solve this, this will become n minus x upon 1 minus p. Solve this, this will become n minus x upon 1 minus p equals to x upon p. So this will be, I wanted to estimate the parameter p here. So in this case, it will be p upon 1 minus p equals to x upon 1 minus x, right? I think we done something. So x here is what actually? So I think we shouldn't write x, right? Because x may be looking like this x. This should be, let's say, some a or something, right? A or something. N is total number of trials. A is means A means, or if you understand this, x means what actually here, number of
It's
times
the number of successes.
successes we have found in the sample, right? Out of n.
Yes.
So if you are okay with this, then we can keep this as, you should not, this x is not belongs to here, right? Correct, right? Just think about it. Otherwise, this will create a problem. Okay, so p upon 1 minus p.
Fine.
Hmm?
It's fine, sir. I mean, it's the derivation, right? So we can just replace x by anything when we are doing it. So it's fine.
So yeah, so let's. I think what you can do is we'll write this down. Maybe 1 minus p upon p, and minus x upon x. So I can definitely write this minus 1 upon p n upon.
So we can just cross multiply, sir. Cross multiply n minus x by 1 minus p is equal to x by p. You can just cross multiply and cancel.
Hmm. Yeah, okay, fine. So this is okay, right? So yeah, I did like, I don't know, some
Yeah, p is equal to x by n. Yes.
p equals to x by n. So this is p is not, this is a p hat. P hat means this is the
p.
estimated parameter. This is not the actual p of a distribution, right? Of the population, I'll say. This is, we have found out by using the sample. So maybe we'll see one example of it. Maybe
So this x is the number of
number of suc-
uh,
yeah,
successes. Okay.
in a sample. Okay, and this n is total number of samples. So we'll see one problem of it. I'll show it. Suppose we have this problem. Let's say we have head, tail, tail, head, 1, 2, 3, 4, 5, 6, 8, 10. Okay, this belongs to some Bernoulli p p. Okay, I wanted to find the p hat. So what I'll do is, and I'll say head is a success. In that case, from the previous derivation you have seen, what should be my parameter estimate of this? So it is number of successes divided by total number of, so total number of trials is, or maybe the number of samples is how much? 10, right? And 1, 2, 3, 4, 5, 6, 6 success. This is zero point 0.6. If you wanted to find it using, so if you wanted to find is using the derivation, maybe if you wanted to derive it, how do you do that? So I'll find the likelihood. In this case, I'll say p is equals to what?
P raised to 6, 1 minus P raised to 4.
So let's say it's p raised to 6, right? Because I'll write like this, right? Product of all the PMFs. So p into 1 minus p into 1 minus p into p into 1 minus p and 1 minus p, like this, right? So this will become p to the power 6, and here it will become p to the power 1 minus p to the power 4, right? Then what will be log of L? So this will be 6 times p plus
6 LNP, right? Log is there.
6 log of p, right? Sorry, log p plus 4, and negative will be what? This. And if I differentiate this negative log with respect to p and equate it to 0, then it will become minus 6 upon p uh, minus 4 upon 1 minus p minus 1 equals to 0, right? So this will be, if I go here, it will be 6 minus 6p equals to 4p. So 6 equals to 10p, and p will be equals to 6 by 10, which is 0.6, right? So This is the same thing which we have seen. So if you have given the sample like this, if you have given a sample like this, then you know how to find the parameter estimate. So in general, also for a discrete case, you can do like this, and for continuous also, it's not a different thing. Okay, so let's try to see for exponential. So we'll see the general case. So let's say x1, x2 to xn are from exponential. Okay, how many parameters are there in exponential?
Lambda.
One parameter. Right? Done. Okay, so and what is the PMF? So PDF.
Lambda e raised to minus lambda x if x greater than equals to 0.
X is sorry. Let's see. Right. Okay. So what will be the likelihood here? It's a product of all this, right? All these PDFs. So it will be lambda e to the power minus lambda x1, right, into lambda e to the power minus lambda 2, sorry, lambda uh, x2, like this, right? Okay, so in the compact way, how can I write this? Lambda to the power
Lambda raised to n.
n,
N.
then product of,
And
or okay, fine, e
so
to the
we
power,
could
I can
write the
write, yeah,
summation in the power, right?
fine, yeah, that is also okay. So it will be e to the power minus lambda x1 plus x2 to xn, correct? And that I can write in the compact way as e to the power minus lambda sum of I equals to 1 to n
xi.
xi. Fine, this is my likelihood. So what will be log likelihood? It will be n log lambda, right? Plus or minus lambda more I equals to 1 to n. Okay, and log of e is 1, right? Because it's natural log. So ln of e is equals to 1. Now negative will be what? Like this. And if I differentiate this, okay, you can have, I'm telling you, you can have some other method also. You can do like whichever you feel simpler, you can do that. So here it will be minus n upon lambda, uh, and we have to equate it to 0, right? So yeah, so minus n upon lambda uh, plus,
It's the summation part only.
hmm? Sorry,
So the summation part only, right?
sorry,
We are
sorry.
actually maximizing lambda.
Yeah, I have to write like this. So here we are minimizing, right? When I say negative likelihood,
Ha ha ha. We are minimizing, yes.
right? So yeah, so it will be minus n upon lambda. Then this will be summation of I equals to 1 to n xi, and which is equals to 0, right? So left with summation of n, which is equals to by lambda. So we are actually finding the estimate for lambda. So it's lambda hat will be equals to what? N divided by.
It's
So it's the inverse of sample mean,
in sample min.
right? So this is the case for. So let's say you have given some parameters. So let's say 1, 1.5, 2. I don't know. Okay, I'm just giving you some numbers. Okay, I'm not sure about those numbers. 4. Let's say these are from exponential family. Okay, exponential uh, lambda. In that case, how do you find the lambda hat? What will be the lambda hat here? The lambda hat will be what? Equals to 5 divided by.
5 by the sum of the samples.
Right. That should be your answer. And this kind of questions you can expect in the exam, right? But see, that's what if you don't know the end result of it, I've shown you how to find by using the derivation, right? You just find the likelihood first, then you can find the negative of log likelihood, and then equate it to 0. Then you will get the parameter estimate. Okay. Okay. So 2 3 things we'll see quickly, and then I think still we have left with some things, right? Like Gaussian mixture models. Okay. Okay, maybe Gaussian mixture model you can ask in the tomorrow's lecture. Okay, I'll just write down the Gaussian mixture models. I think that also we have seen in stats too, but that was not the Gaussian mixture model. It was like Sir has shown you like this, right? The continuous with respect to discrete, right? One is discrete and one is continuous. How to find the joint density of those two random variables, right? We have seen the joint density of two continuous, the joint density of two discrete, and joint density of continuous and discrete. So Gaussian mixture model, which we have seen here in this week 12, is kind of similar to that we have seen there. Okay, so at this, I'll just briefly explain law of large numbers. So that part, okay, law. So there are inequalities we have to check about, which is one is Markov inequality. So what is Markov inequality? And okay, first of all, this is applicable for is applicable for only
Non-negative random variables.
positive random variables or non-negative. Okay, and what is it? Let's say probability that x a random variable is. So generally, these inequalities tell us how far the value taken by a random variable from its mean, right? From the mean of a random variable. So let's say x probability that x is greater than or equals to t is equals to what? Mu upon.
So it's less than or equals to upper bound, right?
Okay, so it should be less than or equals to mu by t. Okay, so what is mu here? It's a mean of the variable x. Okay, if I have a problem, I'll just write down the inequalities. So maybe you can see the questions tomorrow. You have the solve with this class tomorrow, right? You can see the questions on inequalities tomorrow, maybe. Okay, let's write down all the inequalities. Okay. Chebyshev. So this is also the similar as that of Markov, right? You can see the different the derivation in the lecture. You will see that. Okay. So it is not important anyway, but still, if you are curious, then you can check the derivations there. So this is applicable for what? For negative random variables also, right? This is applicable for positive as well as negative. Okay, let's say x is a random variable, okay, and it is having, let's say, a mu as a mean of x and sigma square as the variance of x. Okay, in that case, the probability that the value taken by a random variable is away from its mean uh, by some value t is less than or equals to how much?
Sigma square by t square.
Square by t square. Okay, so sigma is the variance of that random variable, and t is like how much away it is from. So generally, it will be asked for like what is the probability that a random variable is away of one standard deviation, right? So let's say one standard deviation means um, what will be the value then? Let's say if it is k sigma, so k is equals to 1. So what is the probability that x minus mu is greater than or equal to sigma? So 1, right? Like so k generally it will be like we
So
want to
it's like k sigma, right? I mean, the formation
yeah.
is k sigma less than equals 1 by k square.
So it will be then if it is k sigma, in that case it will be 1 upon k square, right? This probability that x minus mu, This also the same as of this, right? So,
Yes, sir.
right? 1 meter. So we have some variations of this Chebyshev inequality as well, but so we are see. Uh, I'm not going into the weak law of large numbers, but the important theorem I'll see is central limit theorem. Okay, central limit theorem. What is this says? What is this central limit theorem? So let's say if we have drawn some random, if we have drawn some samples from height distribution x, then so suppose y is the sum of all this thing. Okay, it's not only sum, right? It can be anything, but generally, if it is a sum of all these samples, in that case, what it says, the central limit theorem, probability that hmm,
So it's y minus ey.
y minus
Expectation of y.
yeah. So
It's actually x minus n mu by n root n sigma, or x n bar minus mu by
okay,
sigma by root n, something, anything we can take.
x n bar is y only, right?
Yeah.
So suppose I'm saying y. What is expectation of y here? It's mu only, right? Let's say
Yes.
expectation of each xi is mu. In that case, expectation of y is what? Because it is n times mu
N
upon,
mu by n.
so it is mu, right?
Yes.
And what is the variance? Variance is not needed here, but okay. Let's say what is variance of y? It's sigma square by n.
So variance is needed, right? We have to divide it by sigma by root n actually. I
Okay,
mean
sigma
standard deviation.
n. So in that case, what it says, the so y minus uh,
Expectation of y divided by variance of y.
variance or standard deviation.
Sorry, standard deviation. Sigma by root n. Yeah. Standard deviation of y.
So it is greater. So this actually is called as z, right? Standard normal variate, right? So uh, it's equals to, or it's greater than or equals to what? Okay, but I don't know. Is there a formula or but this is actually this distribution actually corresponds to what? Maybe I'll say this z.
Sir, is this sigma by root n or root of sigma by n?
Sorry, sigma by root. Sorry, it should be the standard deviation, right? Yeah, it should be sigma by root. Okay, and this corresponds to which distribution? Normal 0, right?
Yes, sir.
Okay. Yeah. So all these things are there. So you can see the problems from where the Markov inequalities, Chebyshev, and central limit theorem. So these problems you can uh, you know, target. One more thing is maybe you can expect those problems from bivariate and multivariate. Okay, Gaussian mixture models we are left with. Maybe you can ask it tomorrow. But I'll suggest that don't ask for derivation or something. Uh, you can understand that by the example itself, because whatever is there in the lecture, it's slightly confusing. I guess the notation, not confusing, but the notations are very new, so it may be very difficult. So it's better to understand by through the examples. Okay. I think yeah, and so for your anyway end term is coming so near. So the more important chapters will be 9, 10, 11, 12. Okay, this is like kind of more weightage to this. You have to work with week 8 to 1 to 8 with maybe I'll say moderate. So week 1 to 8, just whatever the questions are there, you just go through them once. Yep. I think you'll start the revision anyway next week, but still I'll suggest.
But we are getting like very limited time for the final weeks. Like
Uh,
almost like
yeah, I
from
understand, but I
like
hmm,
not just this subject, like all the subjects. From like last 10 days, we are having to cover like 4 weeks. Today is the submission date for week 12 for most other, like only MLF has like Friday. Every other subject it's today. 11 and 12 we have to submit
today
today.
how come?
Yeah, that's how it is for other subjects.
How many
And
subjects have you taken this term?
I have three subjects.
Which one?
One project. I have MAD one project and MAD one, then DBMS and this MLF.
DBMS, MLF, and MAD1 project. Huh?
MAD one and MAD one project.
Oh, MAD1 subject also.
Yeah.
Uh, DBMS, MAD1, and MLF. Okay, so it's like wide variety of subjects.
Uh,
It's not interconnected as
no.
okay.
Uh, but like
One is purely mathematical, you can say, or and others are
yeah.
okay. I don't know how we are managing that.
Uh, so the thing is that like we got like last submission was on Friday, right? For
Mm,
week 10.
mm.
And this 5 days you have to cover like 2 weeks. And same for like all subjects. Even MLF we have to cover it like if you are taking quiz 2 up to week 8, it was on 3rd. Today is 13th. So in 10 days you are having to cover 4 weeks.
I understand. It's difficult, I know, but that's what I'm saying. That maybe try to solve the examples. Okay, that's better. Better trick is here because the 11th, 12th week is, we have seen enough in stats too, right? Not many concepts are new here. Uh,
But the sir is the thing is like in stats to be like what all we gonna get here like so everything is studied in stats too. It's pretty much in these 2 weeks, right? Like
yeah,
everything is pointed here like so what all are like the important like what all we can skip and or maybe we can.
I understand. Okay, it's difficult. I know. Maybe. Uh,
Because we can't study the entire stats too in this 1 week, and we hardly get time to revise all those. So at least some important topics, if we
maybe
are
maybe this happens, right? I will tell you like which all questions, maybe which topics
topics.
you have to cover, right? You
Yeah.
should not you should not study all the topics. I'll say don't go into the derivations much. Just see, but okay, Markov inequality will be important. This Chebyshev inequality. So try to solve the problems. Markov Chebyshev, you don't get much of the things, right? And central limit theorem is also there. Mm, okay, maybe I'll tell you guys the topics. Okay, which are the important topics from at least week 11, 12. I'll tell because I understand it's uh, very difficult to go through all these topics. Maybe you can study it later also, right? But I'll tell you which topics and which questions from like which topics you should consider with respect to the end term. Okay, but I guess all of you guys have like good quiz too, right? The results are good, so maybe. But I don't know. The quiz one was not that good, so it's fine.
Like
Sir,
maximum
N1
percent,
contributes.
yeah, it will be like 60% of the grades comes from
Yes,
it.
end term. Right, right,
Yeah.
right. Okay, I'll tell you. I'll tell you the topics from 11.
The thing is like if you don't like you are not studying in deep like if you're just
Hmm. Yeah,
solving
I
for
understand.
some
So
problem
I think all
and
of you
then
have done
in
enough.
the case like there is always one question that's like edge case kind of question, right? we have to like it will be usually for 3 marks or 4 marks. There'll
Mm,
be like one question where just like superficially knowing isn't enough.
mm. Okay, fine. No, if we tell if at all that type of question is there in term, I will tell you. Okay, so I'll tell you which topics you have to, at least for week 11, 12. I'll tell you. Other topics you have to study. So I think from quiz 2 onwards, it's 9 and 10th week, right? Which is optimization. So until 9, I think it is still fine. Week 10 is you have to study a bit. Linear algebra part, you guys have to again revisit. I don't know if you guys remember everything. It's fine. If it is not, then you have to go through SPD, PCA. PCA, I don't feel it is difficult, right? If you go through the steps, it is fine. So, how many of you solved PCA properly? The quiz two. It was good. Okay. Okay. So PCA is okay, right? Like PCA, I think the steps are there. Nothing different is coming. Right. 11, 12, I will tell you. Okay. Fine. Next week I'll tell you.
Okay, sir.
Okay.